in this lecture we are going to see moment generating function of a random variable. As we proceed in the course, we will see that moment generating function actually is a very important and useful tool in probability. So what is moment generating function? Moment generating function is nothing but the expectation of e to the power tx is called the moment generating function of x at the point t, provided that this expectation exists in a neighborhood around the point 0. Okay, so provided there exists a real number a greater than 0 such that the expectation exists for all t belongs to the interval minus a to plus a. So that means basically this expectation exists in a neighborhood around the point 0. So that means basically moment generating function is nothing but I take the function e to the power tx, gx equals to e to the power tx, and then I take the expectation. Okay, so now notice that this particular condition that moment generating this expectation exists in a neighborhood of 0 is quite important, and the reason why it is important we will see within few minutes. So let us first start with the computation of MGF of three distributions. We start with the binomial distribution. So for the binomial distribution, we know that the probability mass function is NCX p to the power x 1 minus p whole to the power n minus x. So in the parameters are n and p respectively. So if I try to find out what is the expectation of tx, which is basically which is summation x equals to 0 to n e to the power tx into the probability mass function of the binomial distribution. Then we make some algebra here, that we club these e to the power tx and p to the power x together to write p e to the power t whole to the power x. Then again we get a binomial sum, and using that this summation is nothing but this quantity 1 minus p plus p e to the power t whole to the power n. Now notice that as this is a finite sum, the sum exists, and this exists for any value of t here. So that means this expectation exists for any value of t belongs to R. Okay, one point I should mention in this case, notice that e to the power tx is always positive for all value of t, all values of x. So checking the whether this expectation exists is same thing to check whether this sum is finite or not. Okay, so that means we have already shown this sum is finite by calculating it, and so we can say that this expectation exists for all t belongs to R. So in the definition, this a I can take any a greater than 0, does not matter. For any a greater than 0, that for all t belongs to minus a to plus a, this expectation exists. So the moment generating function of binomial distribution exists for any t belongs to R. And in these cases, we generally write that the moment generating function of x is given by this expression for all t belongs to R. We do not specify what a is because it is true for all a. So we write that x belongs to R. Okay, here, hope that this point is clear to you. The computation of the moment generating function is clear to you. What is the use of the moment generating function? As I already mentioned, we will come. First, see how we can calculate the moment generating function. Next example, the example of the distribution exponential with parameter lambda, exponential with mean 1 by lambda. In this case, the expectation of e to the power tx is same as lambda integration 0 to infinity e to the power tx e to the power minus lambda x. So lambda e to the power minus lambda x is basically is the density function multiplied by e to the power tx, which can be written in this form. Now notice that this integral converges, or this integral finite if and only if this part is strictly positive. Right? This integral is finite if and only if lambda minus t is strictly positive. That means this integration exists, or this expectation exists if and only if lambda is strictly less than 0. And in that case, the moment generating function or expectation of e to the power tx is given by this expression 1 minus t by lambda whole to the power minus 1 for all lambda t less than lambda. This one is very important in this case because in this case this expectation exists only for t less than lambda. So the writing the range of t is an important part of writing the moment generating function. Now you see that as lambda is always positive quantity, So I can take any a which is less than or equals to lambda, and in particular I can take a equals to lambda, and I can write that this expectation exists for all t belongs to minus lambda to plus lambda. Does the moment generating function of x exist? And it is given by this. Again, in general, we do not write that t lies between minus lambda to plus lambda or some minus a to plus a for a strictly less than a strictly greater than 0 and less than lambda. Generally, we write the whole range like this: t is less than lambda. Okay, clear? So for the exponential distribution with parameter lambda, the moment generating function is given by 1 minus t by lambda whole to the power minus 1 for t less than lambda. Let us consider another standard distribution which is normal, and again the calculation is almost same, that e to the power tx can be written as minus infinity to plus infinity e to the power tx multiplied by probability density function. And once you do the algebra you just take it here, simple algebra, you will get the expectation of e to the power tx turns out to be e to the power mu t plus half t square sigma square. And in this case, this integration exists, this integration is finite for all values of t belongs to R. That's why basically moment generating function exists for all t belongs to R. And so that is written that the moment generating function of x is mxt equals to e to the power mu t plus half sigma square t square for all t belongs to R. Okay, fine. So I hope the computation of the moment generating function is fine with all of you, and this is nothing but finding out the expectation, finding out the some function of random variable x. That's all. And only thing is that I have to be a little bit careful about what range of t I can write the moment generating function. Okay, next theorem, which I will not go into the proof, but okay, I will go into the intuitive proof. That will not be the exact mathematical proof, but the intuition I will give you. But the statement of the theorem is very important. What does theorem basically says? Theorem basically says that if the moment generating function of a random variable x exists in a neighborhood of the point 0, then the derivative of all order of the moment generating function with respect to t at the point 0 will going to exist. Okay, so moment generating function actually is a function of t. So the derivative of the moment generating function with respect to t at the point t equals to 0 exists if the moment generating function exists. And the most interesting part is that if I take the kth derivative at the point t equals to 0, that is nothing but our kth raw moment. So that means kth raw moment can be computed from the moment generating function. Note that I have to take kth derivative and then I need to put t equals to 0. So basically at the point t equals to 0, I need to take the kth derivative. Okay, so putting t equals to 0 is important here. So that means from the moment generating function I can find all the moments of a random variable, and that's why the name moment generating function is given to the expectation of t to the e to the power tx. Okay, so from where the moment generating function comes, I hope you have understood that from moment generating function I will able to compute the expectation all the moments, all order moments of a random variable. Now another point. Okay, now another point I should mention here. Note that in this case, this thing is necessary, that moment generating function exists in the expectation of e to the power tx exists in a neighborhood around the point minus a to around the point 0. Okay, the expectation of e to the power tx exists around in a neighborhood of the point 0. That is important for this particular theorem because I have to finally take the derivative at the point 0. That's why this is important, and this is one of the reasons why we put that in the definition, why we put the condition that we say the moment generating function exists if this expectation exists in a neighborhood around the point 0. Okay, this is one of the reasons, and then the next theorem we are going to discuss, we will see that there also we need the same condition. So moment generating function actually helpful if expectation of e to the power tx exists in a neighborhood around the point 0. So that condition is itself given in the definition. That is the only reason why we keep this condition in the definition. Okay. So now the next thing we are going to discuss is technique 3 of transformation of the random variable, and this technique actually based on the moment generating function. So what is that technique? How we can use the moment generating function? Well, to do that, first we need a definition which is basically the definition of same in distribution. What do you mean by same in distribution? So two random variable x and y are said to be same in distribution if the distribution function of x and distribution function of y, or cumulative distribution function of x and cumulative distribution function of y, they are same for all x belongs to R. This condition is important, that all x belongs to R. Okay. So if two random variables distribution function are same throughout the R, then these two random variables are said to be same in distribution. Or in other words, we sometimes say that okay, x and y have the same distribution. Clear? So same distribution means the distribution functions are same over the whole real line. And the notation we are going to use, that x and y are equal in distribution. Okay, x and y are equal in distribution. This particular notation we are going to use. Now let us talk about theorem 2.14, which is basically important theorem and main theorem for technique 3. It says that let x and y are y be two random variables having moment generating function mx and my respectively. So x and y are two random variables. The moment generating function of x is mx and moment generating function of y is my. Then if there exists a positive real number a such that moment generating function of x is same as moment generating function of y for all t belongs to minus a to plus a, that means in a neighborhood of around of the point 0, if both the moment generating function are same, in a neighborhood around the point 0, if the moment generating function of both the random variable are same, then x and y are same in distribution. So x and y in that case have the same distribution. Clear? So if moment generating function of two random variables are same in a neighborhood of the point 0, then the distribution of that two random variable is going to be same, or cumulative distribution function is going to be same for all values of x. So they are same in distribution. The random variables are same in distribution. Okay. Now the proof we cannot give, but this is a very important theorem. But one thing keep in mind, see, in general for some function, if expectation of f of x is same as expectation of f of y, that does not mean that x and y has the same distribution. So moment generating function is a very special in this respect, that if moment generating function are same in a neighborhood of the point 0, the distribution of both the random variable is going to be same. But this is not true in general. But obviously, if two random variables have the same distribution, then expectation of any function of x is same as the expectation of that function of y. But this equality in general do not imply this equality. Okay, I hope this point is clear. So let us see one of the examples where we can use the moment generating function to find out the distribution of a function of a random variable. So we start with a normal distribution, normal with mu sigma square. So x has distribution normal with mu sigma square. And suppose we try to find out what is the distribution of y, which is a linear function of x, a plus bx, with the condition that b is not equals to 0. Because if I take b equals to 0, that means basically it is constant plus a, and that is basically a trivial case. Okay, or sorry, if I take b equals to 0, then y turns out to be a constant one. So this is a trivial case. So that one I am not considering. We are taking b not equals to 0 and we proceed. So what I am going to do, first I try to find out what is the moment generating function of x. So moment generating, to calculate the moment generating function of x, I need to calculate expectation of e to the power tx, e to the power ty. And then I replace y with the expression of y with the y in terms of x, which is a plus bx, and then just write e to the power ta multiplied by e to the power tbx. So this turns out to be that one. Now this expectation part is nothing but moment generating function of the random variable x at the point tb, right? This expectation part is the moment generating function of x at the point tb, and that's what I have written here. Now I know what is the moment generating function of x, that we have already calculated. And we have seen that the moment generating function for a normal mu sigma square distribution turns out to be e to the power t mu plus half sigma square t square. So this is at the point t, but we have to now write it at the point tb. So all the t here will be replaced by tb. So that means this quantity turns out to be expectation of e to the power tx ty now turns out to be e to the power ta into e to the power mu tb plus half b square t square sigma square, which can be written in this form. Now notice that this is in terms of the moment generating function of a normal distribution. So if I take z, which follows normal with mean a plus b mu and variance b square sigma square, then the moment generating function of z is exactly this one. So that means the moment generating function of the random variable x and random variable y are same for all t belongs to R. Okay, so moment generating function of a, y and z are same for all t belongs to R. I can use the previous theorem, and using the previous theorem I can tell that the distribution of y is same as distribution of z, and we know the distribution of z is this one. That means distribution of y is also normal with the parameter a plus b mu and b square sigma square. So this way, using the moment generating function, I can find out the distribution of a function of a random variable. Obviously, one trick is here. One tricky point is here. Okay, first tricky point is basically two tricky point is there. First tricky point is that I need to calculate this expectation explicitly, and once I can calculate this expectation, then I need to find out this moment generating function corresponds to which distribution. This inverse mapping we need to understand. Okay, so moment generating function, see, if I given with a distribution function, the PDF or PMF, most likely, I mean, in principle, I should be able to find out moment generating function if it exists. Obviously, that the summation by or integration could be very difficult, or maybe explicitly we cannot able to find it out. Those problems could be there. But when even I find it out explicitly, then the next point is that how I have to understand this moment generating function corresponding to which distribution. If I cannot understand that, then I cannot take which distribution for z I have to take here. Okay, so this is an important thing, and my suggestion and I keep it as a homework. Find out the moment generating function of all standard distributions which we have discussed till now. Okay, three of them we have already did here, that binomial, exponential, and this normal we have done here. The others, for example, Bernoulli, binomial, Poisson, then gamma, beta, uniform, those things. Please find out the moment generating function of these distributions and try to remember them. Okay, with that I stop in this lecture. Hope that the things you have understood. Okay, thank you for listening.